Hello everyone. In the fourth day in a row in a Dotnetos Week event, which is all about .NET, we try to provide you interesting content about .NET. So this is the fourth day of our initiative. And just a few words of general description. This is a .NETos Week. Such initiatives are always supported by some partners, and now we have those partners, which is KMD and Demand Technology Center, and without them it would be much harder to make this event to happen. So thank you very much to them for supporting us, providing you this content that you can watch all this week. And this week is called, as I said a few times already, .NETos Week. We are in the past the middle. So we have Naomi Stevens on Monday. We had Martin Hoppe. We had yesterday a discussion panel about .NET in general, and today we have Sebastian Solnica that he will introduce himself in a moment. And tomorrow we are ending with Steven Taub, which will be also talking about .NET performance and internals and all this stuff, which is so interesting for us, and I hope for you also. If you like our initiative, if you like our videos, please subscribe, because then we will be able to be noticed about other initiatives, other themes, and other stuff that we provide to you. So that's all talking from me, because the most important part obviously today is Sebastian and his talk. So let's see Sebastian. Let's remove the slides. And hello, Sebastian.
Hello, everyone. Yeah,
Nice to see you. As I said, I'm just going to the background. I'm not important here today, so the scene is yours. Please introduce yourself and enlighten us about some hard stuff.
Okay, Conrad, please share my screen if you can.
Yep.
Okay, thank you. So hello, everyone. I hope you enjoyed the .NETos Week so far. I'm very happy to be a part of it. My name is Sebastian Solnica, and in the internet you can find me by using my nickname, Low Level Design. And I also have a blog at lowleveldesign.org. And today I would like to talk about tracing. And my point in this presentation is to show you that tracing is not necessarily connected with troubleshooting. I mean, of course, that's often the main reason why we trace, but it's also a great way to learn about how things work internally. And when we think of tracing or debugging or troubleshooting in general, we think of either tracing or debugging. So I will start with some general information about tracing. Then we will move to tools that I consider the most useful. Maybe not the most useful because there's a lot of them, but some of the ones that I really like. And then we'll look at .NET tracing and APIs that are provided for us to write diagnostics tools. So first we'll start with differences between tracing and debugging. The first one is that tracing is usually non-invasive and generates low overhead on the system where we trace, while debugging is quite invasive. As you know, we are stopping the application, we are freezing threads, and well, we have a big impact how the application executes. Another difference is that when we are tracing, we are not stopping the application, but the application runs and we receive events. So all the data that we have for troubleshooting or for checking is within the events that we receive. So when we trace, it's really important to collect right events at the right time. When we compare that to debugging, when we are debugging an application, for instance, we stop an application with a breakpoint, we have access to the whole state of the application. So we can examine the memory, we can check the state of the threads, we can check the call stack, and so on. So that's a really big difference, and that's why tracing in tracing we all need to remember about filters and configuration of the tracing session. And the last difference is that tracing is usually safe to use in the production environments. So we can trace, it's connected with the first point because it generates low overhead. While debugging, if we need to debug in the production, we usually are quite desperate and we need to solve really severe issues. So that is not probably recommended. And when we talk about tracing and debugging, the next important that applies to the subject that applies to both tracing and debugging are symbols. And usually the slide about symbols is quite boring. It just needs to be said. But today I would like to make it a bit funnier. First, why we need symbols. So for native code, of course, we need symbols to see the names of the methods that are on the call stack. And in native code, PDB files, so the files that have this dot in the icon, it used to be a red dot, now it's a gray dot. But those files used to be just maps between the relative addresses that are in the executables, and those addresses were mapped to some source files or names. When we have public symbols, not private ones, then we will only see names for the methods. With .NET, it's a bit more complex because we have the just-in-time compiler. So we have intermediate language offsets that we need to match to source files. And then we need to match the native code, which is executing, to those IL offsets. So .NET compilers are using sequence points, and I have an interesting example how you can actually fool the debugger a little bit. Here I have a very simple application, as you can see, but I'm referencing a library which I generated, and we'll look into the source code in a moment. It has some PDB file, and when we start, this example could be a funny joke for another developer, maybe not necessarily in the production application. But if we now start stepping through the code, it just starts. But if you press F11 and then go into this method, we are presented with some txt file. And so although we are debugging the .NET application, we are landing in some funny place. And of course, the stepping away, we can step away. But the thing is that we fooled the debugger by using a sequence point, which does not necessarily match the valid source code in C#. So how did I do that? How did I do that? The important library is, I need to move to the right folder. That's the generator. And its source code is quite simple. I'm using an anet API. And here we are building the assembly. And the important thing is here we are creating a PDB file, so something called symbol document writer. And this document writer, I mean, we can mark a sequence point in a code which we emit. That's the whole emitting part. So we are looping through the content file, which is this txt file, and then we are creating a sequence point for this simple line. So in fact, that's the line which is behind the line that you saw in the txt file. So it's just a simple example how you can play with the sequence points and how they are emitted in assemblies. And another important configuration for symbols, that's for the whole system, is that we need to have, I mean, it's a good advice to have a global environment variable for caching public Microsoft symbols. If we are debugging, of course, on Microsoft, that won't work on Linux. But if you are on Windows systems, then define this variable, prepare some cache folder, and then pointed to this public address for symbols. And what's great is that Visual Studio recognizes this variable. So if we have options here, and then we go to debug, where is it? Debugging, we'll see that the variable will be here, and we only need to enable the source server support, and you will debug the source code that Microsoft published. So, for instance, for .NET, it is right now it works really great because we can step into .NET internal methods. Next, I would like to group the sources of trace events that we have. So there are, I group them into two categories. The first one is kernel mode, so events emitted from the kernel. And then we have user mode, so events emitted from the user mode. And when we think of the kernel mode emitted events, I think there are generally two places. The kernel itself, so those are the system providers, such as, for example, the profiler for a CPU, so those events that are emitted every few seconds, the dispatcher that also works in the kernel mode, or the scheduler. And then we have custom drivers. So for instance, if we have a specific file system driver, it can emit some events that we can collect and later use for diagnostics. For user mode, we have application custom providers. So for example, .NET providers such as GC or just-in-time compilation. Those are the providers that .NET gives us. But we also can create our own providers, and I will show you that in a moment. And we also can use hooks in the applications. I won't be covering this one, but because that's actually quite invasive, we need to inject some code into the application. But that's quite similar to what profilers are doing. So hooking into the method entrance and method exit. And when we think of those system providers, I need to mention the system APIs for collecting events. So on Windows, we have ETW, so event tracing for Windows, which we'll be using in a moment. On Linux, there are a few different technologies. And if you remember, for .NET Core, we were advised to use a script perf collect, which was based on LTTNG and perf. But right now, I think that eBPF is gaining a lot of popularity. I won't be covering Linux Linux system tracing in this session, but you might have a look at Brendan Gregg blog. He writes a lot about it, and that's a really great source of knowledge on Linux system tracing. And so that's all for the general part. I will move to the first tool that I would like to show you, and it's one of the tools that I really like and enjoy using. It's one of the best tools in the sysinternals suite. So if you're using sysinternals, maybe you're using Process Explorer, Process Monitor is just as important, or I think it's even more important. It allows us to collect events for file I/O, for file system activity, a registry, network activity, and some profiling events such as process creation, thread creation, and also it collects those regular ticks when a process is running. And when we start Procmon, it immediately collects events for our system. As you can see, a lot is happening on a system in every second. But I would like to show you how to filter, how to find yourself in those events that Procmon shows. Actually, a presentation about Procmon could be for an hour or more, but I will focus on one particular example. So here I would like to show you how buffering works. And I created a very simple application in Linkupad where we randomly generate random amounts of ASCII characters between 1 kilobyte and 2 kilobytes, and we write them to a txt file, which is in the same folder as this linkupad query, and it's named test.txt. I will start this application. It should show that, yeah, it started writing some events. And in procmon, we will define the first filter that would be for the process name. I know that linkupad queries end with query exit, that's the process name. And I will also add one really great filter, and I will tell you in a moment why it's really useful and great. We'll define category, we'll set a filter to category is right. And this filter, if we add it, and now we will start tracing, we should see that the requests coming from the linkupad. And those are the requests that modify the system. So when we pick the category right, we actually asked procmon to show us only the events that are changing anything in our file system. Of course, sorry, not in the file system necessarily, but registry too. So all the events that are modifying those components of the operating system. So when we look at what is happening, we can see that the numbers here are quite random. But here we can see that the file stream or the stream writer, which is using file stream under the hood, is writing blocks of 4 kilobytes, which is not surprising because that's the default block size for NTFS. So that's one of the optimizations that FileStream has, is that it's buffering the bytes that we are sending to it. And without looking into the .NET source code, we can easily see in procmon what's the buffer size. Okay, I can stop it. And why the category filter, this one is great. Another reason is that imagine that you have an application that is supposed to write a log to some place, but then you start it and you don't see the log. So where did it write the log messages? With procmon, you can easily find it. You just define this category and then look for it. Similarly, when you have an installer that you need to, that is failing or has some problems, you also run procmon, look at for either the log files, or you can check what the installer is actually modifying in your system. Additionally, procmon has a really nice process view. So when you're tracing and one application started and during the trace or end, okay, all of them are actually running. But I can start the trace, start Notepad, and close it. And we should see Notepad in the tree. Okay. Never mind. Sometimes there's a bug when procmon is running, when we had a trace previously recorded. So the important thing is that we can filter, we can create a filter for all the process and all the children. So for example, you might, this way with procmon, you can debug you can check what is happening during the build process, for example, what the MS build is creating. So all those kind of scenarios. And I will only add that you can also trace the boot process of Windows to learn what is happening. And there's one more filter that I would like to show you, or not here, but in tools, there is a count occurrences window. There are lots of statistics that are worth exploring, but here is also the result column. And okay, but for that, I might remove the, yeah, that would be better. Once again, count occurrences. I will pick result and then count. And what we will see here, I hope you can see that, is that we have all the results that were present in the table, in the events table. And if we count them, it's quite often those with lower count are those that are creating problems. So for instance, when you have an application that fails, and you recorded procmon trace, you filter the logs for a given application and just look for the events with a low count number, and that could be, for instance, access denied. Then you can filter the events, bookmark the one that is failing, so with Control B, and then remove the filter. So you will know where was the buggy event, and at the same time you will be able to see all the events that happened before. Okay, that's it for procmon. If I highly recommend playing with these tools. Actually, all the sysinternals tools are great, and there is a really nice book about them, troubleshooting with sysinternals. So if you use Windows, if you're doing work on Windows, play with sysinternals. Next tool I would like to show you is so we could think of STrace as something similar to procmon. But in fact, it's not. It's quite the way how it works is different. Although what STrace shows is sort interferes with what procmon is showing on Windows. I have WSL opened here. So STrace is, as you know, a command which we use for tracing on Linux. And STrace is tracing syscalls. So first, what are syscalls? I like to think of syscalls as sort of a kernel API. So a limited set of methods that allow a user mode application to enter kernel mode. And user mode application needs to enter kernel mode whenever it needs to perform some work, either on the file system, or it needs to send some data to a driver, or even when it needs to communicate with the network. Well, it always needs to go through the kernel. So when a thread starts in our process, when a thread starts this operation, which requires kernel mode, it needs to perform an instruction that's a special processor CPU instruction, and it needs to enter it needs to switch to the kernel mode. And when it switches, it actually moves the protected mode, so the mode where all the processes have those virtualized memory, and one process can't do anything malicious to another process which is running on the same system. It's leaving this mode and it's entering the real mode where it can modify kernel parameters. Of course, we no longer have control over this thread, so this thread is running in the kernel mode. So those are the syscalls, and as you can imagine, if we strace, and I have here a very simple .NET project. I will open programs. Yes, as you can see, that's just a hello world with a read line. But if we strace it and we save the output to some strace file, so I will run it, and in a moment it will finish. So I forgot to say how STrace is working. So STrace internally is using the same API as debuggers, and that's another syscall which is called ptrace. So STrace is also working like debugger in a loop. So it runs in a loop and waits for events coming from the kernel. So notifications about a syscall that is happening. It can actually even modify the syscalls, and so in that way, it's quite invasive. And you can, when you are a stracing application which is performing a lot of I/O requests, a lot of syscalls actually, you will observe a slowdown of the application. So that's not tracing through STrace is quite invasive, but at the same time, it really shows you a lot. So for instance, when we started this .NET process, we can see that there were a lot of syscalls happening. So we can see all the read files, all the libraries which were loaded in the application. In the applications, we have about 13,000 of lines of the syscall traces. So it's really important to create filters when you use STrace. And for instance, imagine that we will perform a small experiment that we will for later. We'll check with STrace which how the diagnostics ports are opened, so the event pipe ports that I will talk in a moment about. So I will enable the network group and then the file group, only those events. And instead of sending the output to a file, I will send it to grep, and I will pick the lines which have diagnostic in their name. And again, .NET run. And if now what we receive is, you can see that there is a Unix socket opened at the path in the temporary folder, and you need to believe me by word that that's the PID of our process. So the name is .NET Diagnostic, and when we exit the application, this port, this socket gets removed. So this is how event pipe. This is how .NET opens the event pipe diagnostic that we later use for diagnostics. Okay, so that's about it for STrace. A really nice tool on Linux, so nice to have it and use it to see how things work. Next one is Purview, which you probably know. It's a huge tool. I mean, it can do a lot. It's based on ETW, so the system API that I told you about previously. And Purview, if we look at the collect window, I opened it with Alt-C, but we can also use the menu here. And if we expand the panel here, you can see how many events we can trace. So we have file IO. I'm not sure if you can see that correctly, but we have file IO, registry. There are various groups of .NET events, and there are also events for just-in-time compiler. Those are all events collected from ETW providers, and there are a lot of them in the system. Actually, Purview even gives you a browser for those providers, so we can look through them. But today, I would focus only on thread time, because I would like to show you how the thread time analysis work in Purview. So we'll use, maybe before I use that, a small difference is that we have two different ways of tracing CPU time. We either collect CPU samples, and those are the events that are happening every 100 milliseconds, I think. So every 100 milliseconds, the kernel sends a dump of all the threads that are currently executing on our CPUs. Of course, if we are tracing this way and one process started and ended before we hit the tick of the timer, we'll not have an event for that. Thread time is much more detailed, and we'll see why in a moment. And what we'll be tracing is just a small application. I have it here. So we have an application that has some async main and is doing an await which lasts for 1 second. And I print the process ID and then thread ID before the delay and then after the delay. Here's this application compiled. I will run it with Shift Enter. Oh, okay, I ran it, but well, I was not collecting the trace. So once again, I'm starting the collection, running the application. Okay, it finished. I will keep this window open so we'll have the PID, and I stop collection. It takes a moment for Purview to finish the merging, but actually we'll see later when we will be writing our own profiler what's happening when this screen here is blinking. Okay, so we have those various windows in Purview for analysis, and when we have those thread time events, Purview shows us this thread time view. And here we can pick our process, which is sleep, and open. Oh, okay. I have a really low resolution, and that's sometimes problematic. And here we can see on what what our process was doing, and those thread times analyses are really exact. I mean, we can easily see how much time the process spent, the threads in the process spent in a blocked time. We also have events for ETW, for the task, from the task providers. So we can see also some, for example, more specific block time, which is await time. And if I select those two here, we can purview at the bottom will show us that yeah, it's roughly 1000 milliseconds. So we can see that that was our task delay. And to show you how that works internally, so we'll understand what those views are about. I believe that when you know how things are working, you better understand what they are presenting. So I will show you how Purview actually generates those histograms. Those are the histograms in Purview. So those of you who haven't used Purview, that's a funny way how Purview presents when events were happening. So for instance, we have this await time. We can actually drill into it. So I can select just this period of time and then check set time interval or Alt R, and you see that we are now, this thing here changed, and we can see that we are now in the last moment, in the last block of the histogram. Of course, we can drill farther and farther, but here we can see that those two interfere. So await time is finishing, and then we have CPU time. And on the call tree, we can actually check what was happening at those given moments. Okay, but moving back to the await time and block time, how it is calculated, I will copy this end time and then move to my favorite window in Purview, which is events. And those are all the events that Purview collected while we were running the trace session. And I will filter that for kernel thread and kernel dispatch. Yeah, those two. And I will pick those two event types. Okay, so the kernel dispatcher ready thread is an event that happens when the thread is ready to run. So for instance, the thing that, for example, the event that the thread was waiting on got set, and it does not need to wait anymore. It can run further. So it just, the dispatcher is dispatching is moving a thread into a ready state. So the thread is ready to run, but it does not yet have the CPU. CS switch is a context switch event. So that's an event that happens when the thread actually gets time on the CPU. So as you can see, that's a very detailed representation of what is happening in a process. So when I also need to pick the right column, so I will take awaken process ID, awaken thread ID, then new process ID, new thread ID, and old process ID and old thread ID. Okay, I will move them maybe that. And I had copied the time interval because of Polish locals. Purview does not look like spaces here. We need to fix that. Here I started, so I'm showing the events, the CPU events, let's call them that way, or maybe actually the thread scheduler or dispatcher events that were happening after this moment. So after our await finished, after our delay finished. And our PID was 24/7 2, 4. So let's look for a moment when a thread from our process got time on the CPU. Already forgot that. Okay. So new process ID will be this this ID. Okay, I think that's the first moment. I don't see it. Okay, so after this period of time, so those are milliseconds. So as you can see here, we have microseconds. After I do not have the ready thread event here because I started the await hub. I mean, the event emitted by the task event provider was after the ready thread event. But here we can find the moment when our process, so the sleep process, got time on the CPU. And if we click on this timestamp column and then click open any stacks or Alt-S, we'll see that, okay, here are several processes that produced an event at this time, but the sleep process, we can actually look at it, and we can see what was the exact call stack when the process got time on the CPU. So in my case, that was the console write line, which was after the delay finished. And we can see, okay, so the thread that got awakened after the delay was this 13396. So if I move back to the call tree here, we can see that that's the threadful worker. So that's the thread where the delay finished, and that's where the process returned. And that's why we see here in the output, we can see that the thread when before the delay was a different one. So what happens next in our process? Let's look also on the awakened process ID if it happens here. And okay, I think here we go. So again, we have we can see that there's another thread which has a different number, so it has 20,000 something. Another thread from our process got is ready to be run. So not yet on the CPU, but ready to run. And then again, we can look at the call stack. And here we can learn what was the event that actually caused the thread which was previously not on the CPU, so which was blocked, which call stack and which other thread caused this thread to be able to run. And here we can see that it was thread, the one that we previously examined. So the main thread, actually not, we'll see in a moment, that's the main thread. If I move back here, you can see that's the startup thread. So the ID here is the same one as as the one that got awakened, and this one is the thread pool thread. So this thread sets some event that's the API, kernel API for setting an event, and that caused the other thread to be ready to run because the other thread was awaiting on that event. So now here we can see that here we have the thread is marked that it's ready to run, and then here we can see that it got time on the CPU because that's the context switch event. So here we can see that the thread was got its quantum time, so its period of time on the CPU. So what purview, that's the manual way how we can look how tasks are working and examine exactly what are the stacks when a task finishes its job or another task starts running. Even if such a simple application, it could be a really interesting experiment to run. So the CPU view here is showing exactly that. That's the manual analysis that I just did. That's what purview is doing automatically, and it's grouping those events and also collecting using some other events such as those coming from the tasks provider. Okay, I can close purview and move back to slides. And I would like to mention some other tools that you can use for tracing, and that's WPR, WPI, so Windows Performance Analysis. I I prefer purview. It could be maybe masochistic on my side, but I just prefer this simple view. Those are fancy fancy tools, but I suppose that they are mostly used by guys who are working on drivers, and well, it just depends. Maybe some people prefer the way how those tools work. You can look at them. Then we have recently published Procmon for Linux. It is based on ETW, on eBPF, and so that the system API for traces on Linux. And it's a really nice tool, but I would say that right now it's in a beta stage. It has some limits. For instance, we can't run it on WSL2. You need to recompile the kernel. It requires some specific version of Ubuntu, but still, it's a really nice tool and a really nice step forward to have a Procmon on Linux. Then I would like to have a private plug. So that's the tool I'm working on. It has a landing page and it's called wtrace. Some time ago, I published a command line tool, and now I'm planning a UI for a cross-platform tracer. So right now, this tool collects live traces of ETW, and well, that's an alpha stage, so I don't have much here to show, but we can, for instance, filter the file I/O, and there will be events coming from .NET very soon. So if you'd like to receive updates on beta and maybe play with this tool, go to wtrace, I call it wtrace.net, and subscribe or just visit this page. There will be some news there soon. And finally, there is Wireshark for people which need to work with network traces. And even if you do not work with network traces, Wireshark is really great. It has dissectors for different protocols. So when you need to debug some problems in the network, you can do that with Wireshark, and you can learn a lot about protocols. So that's all I wanted to say about the system tracing. Let's now move to .NET tracing. And in the old days of .NET, full .NET framework, we have one way of tracing .NET, and that worked on Windows only. And it was based on event tracing on Windows. So the technology that Purview is using for collecting traces. That actually works also with .NET Core. And on .NET Core 2.0, that I think that was the only option. But starting from .NET Core 3, we have those inter-process communication-based tracing. And we already, with STrace, we already saw what is using I mean, what technology is used or what system components are used on Linux. On Windows, I have some processes running, .NET process running, and so it will be quite easy to show you what we use on Windows. We have system.io directory, and then get files, and there is a special path pipe to list. Oh, okay, I need to maybe also filter them. Diagnostics. Diagnostic. Okay, so on Windows, .NET is using named pipes. So those are, we can list them, and we can see .NET processes on the system that are running. So we can list all the named pipes of this specific scheme and the PIDs of the processes. And those are differences between Linux and Windows. But when it comes to the protocol being used, that's exactly the same protocol, and the events are also the same. And we also we have either we use ETW or the .NET, this IPC-based tracing. We can use the same providers and the same keywords, and that's really great, because if you wrote a tool for ETW, it's quite easy to port it to .NET Core. So I actually won't go through. If you will have this presentation, you can check the keywords. Maybe I will click it. So there are many of them. We can trace just-in-time compilation. We can trace GC, and well, there are a lot of documents already available describing all those types of events. And the old name CoreFX, so the traces that are provided by libraries, not necessarily the .NET, the core CLR, but the libraries. There are also many of them. I actually prefer to find them using the .NET Core source code. And if we look for event source class, which we will use in a moment, we can, by clicking here, we can see all the places where this class is being used. And when something inherits from event source, that usually means that it is an event provider. So as you can see, there are quite many of them. And by checking the source code, even in the source code browser, you can learn how many different, about many different places, for instance, from ASP.NET Core, that are producing events that might be useful in your diagnostics. So how you collect those events? We have a .NET Trace tool, which is really easy to use. First, you need to install that. And so you can install that as a global tool in your user folder. And then you simply call .NET Trace collect, specify the PID of a process that you want to trace. Unfortunately, right now it's not possible to launch a process. So you need to you have the process launch already and you attach to it. I know that the .NET team is working on that. I think on Windows it's actually not a problem because you can open the client named pipe and wait for the server named pipe to appear. I think it's more problematic on Linux because when you have the temp folder, you might need to use iNotify to look for new files that are appearing. I'm not sure how they will resolve that, but I hope it will come maybe in .NET 5. And then we specify the providers that we want to trace. And before I show you how it works, let's also look how we can emit our own event. And that's fairly simple. You just need to, like those other classes that we saw in .NET source code browser, you simply need to inherit from the event source. Then you can name your log somehow. Here I name it simple log. And then we need to define events that we will be sending with arguments. And there could be, of course, many arguments here. The manifest for our event is generated automatically. The important thing is that not all types are accepted here. So we need to use the limited set of types that will be properties of our events. And those IDs, of course, must be different because that would mess up the log if they were the same. And I have an example also in Linkupad where I have, first of all, we are waiting for enter because we need to have the PID that we will trace. Then I have this simple event source that I just show you. I have I have those two events that I will emit before making an HTTP request, and the HTTP request I'm making this request to the site dotnetos.org, and later I'm throwing and catching an exception. So something really bad, but it's just to show you something. So let's create a .NET Trace session in PowerShell. I would prefer to have it maybe a little bit higher. Okay. So I will run .NET Trace. Okay, I haven't started the application. So now we started. We can see the PID here, 15992. And we'll specify the providers. And I want my simple log with all the keywords. Then I would like to have the default .NET provider, so .NET runtime, and here I would like the only exceptions, but that's the flag for exceptions. And then I would also like to collect, I don't remember the name, yeah, Microsoft system, sorry, net HTTP. That's the source for HTTP events that might be happening in our process. Oh, okay. I might have misspelled something. Oh, sorry, not .NET Trace. I might have a bug in the slide. 5.9. Oh. One
You
demo
forgot about collect, I believe. You don't
Connect?
have .NET Trace collect.
Ah, right. Thanks, Konrad.
No problem.
Yeah. Okay. Yeah, I was too focused on the providers. Yeah, thanks. That should be it. Yeah, we started tracing. Okay, so now we're tracing. I will. Here we got the response from dotnetos.org. I will finish the trace, and then we can use either we can convert the trace to the Chromium format, or we can open it in purview. As I'm on Windows, I will just open it on purview. It's the net trace file. And in purview, as we have only those specific events that I wanted, there won't be many here, but here we can see our log, so our custom event with our message. And additionally, you see that you receive for free, you receive those default properties that are coming with a trace event, any trace event. But here we can also see a lot of information about what was happening during the HTTP request. And Purview is maybe not the greatest tool to look for those traces. So I created also a tool for that. It's named, I will close this one, .NET trace. And if I run it with this speed again, because Linkupad keeps it alive. Oh, okay. Or maybe it doesn't keep it alive. Oh my God. Yeah, 1 more 5, 3. Okay, and now if we run it, I just print all the HTTP events that are happening. So it could be easier to look through them. .NET Trace is open source and it's on GitHub on the MIT license. But what I wanted to show you is how many different things we can learn about the HTTP request that is going on. So for instance, here we can see all the headers, all the sockets that are being opened, how they are how the TCP connection is opened. We can even dump the content of the packet, of the TCP packet. Here we see that the Dotnetos, actually the details of a certificate, because that's happening on HTTPS, and we can see that Dotnetos are behind Cloudflare and they are using their HTTPS certificate. But what's really important is that we can see, for instance, things that we normally wouldn't see, like there was a redirect. I'm looking for it. Yeah, here. We can see that the Dotnetos.org, in fact, redirected to async-expert.com. And HTTP client, by default, it follows the redirect. It does not show us any information. But by collecting the traces, we can actually see what were the responses, what were the headers. And when you are diagnosing a problem with TLS, so for instance, the certificate is rejected or something like that, those network traces are really a great place to look for the issues. Okay, so now we'll, yeah, there are 5 minutes left, so I need to move faster, but that's the last part of the presentation. When the great thing about tracing is that Microsoft provides us with nugets to play with the API. There is the later one is for ETW events. So we can open our own tracing session and collect events like purview. The first one is for those event pipe events, so those IPC-based events. And there are already some examples available on GitHub or in other places. And some of them are, for instance, Christoph wrote CLR events. That's a great repo with many examples of how to use the .NET Core client and also the trace event. Also, those two repositories, because those are open source projects, they have a lot of examples, so you might look through them. And here's the source code of my .NET NetTrace tool that you can also check to learn how to use this API and write your own tracers and profilers. So the last, sorry. Okay, as I promised, we will, at the end, we will write our own profiler. I can close this one. I have it already opened, and we won't write it because that would probably take more than an hour. But I wrote it already. But we'll have a look how we can use the ETW API. But before I do that, I will show you what this tool is doing. So here I'm in this. The tool is named sampler.exe, sampler because we are collecting profiling using sampling. So the profile method that I mentioned when I was showing you purview. So we can run sampler and trace, and we'll maybe run my sleep tool that we saw previously. So I'm starting the tracing session. Now I run the tool. I finished, and I'm ending the session. And here we are doing the rundown. So that's this part is what was happening when purview was blinking. This blue blink that was happening when I stopped the session. We are doing here exactly the same thing. So we are collecting some additional information. Now we can analyze, and we can pick the process that we are interested in, and then we can pick the depth of the stacks that should be printed. Let's take 10. If we do not say anything, it will print all the stacks, but that might kill the console. So I will pick 10. Now it's working, and in the meantime, we will look into the code. So the start trace, if we are using ETW, we need to be elevated. That's not necessarily true. I mean, we need to be elevated if you want to play with kernel. If we are interested only in user mode providers, it's not needed. So how do we start the trace? We create, it's here. We create the trace event session. We need to specify a name that's unique. And later we define the NT keywords. So every provider, ETW provider, has a set of keywords. So here we are interested in the profile events, so those events that are happening every 100 milliseconds, if I'm not mistaken. And we are also interested in image load events because we want to resolve call stacks. So we need information about the DLLs that were loaded in the process. Then we also specify stack flags. If we do not specify them, then the kernel won't emit the ETW events for containing the call stacks of our events. So then we enable the kernel provider with the keywords that we picked. And we also, if we want to resolve .NET call stacks, we also need to enable the .NET provider, actually the just-in-time symbols, with only the just-in-time symbols keyword. That it does not emit many events. It's just for the just-in-time blocks. So we will be able to resolve, we will know the addresses of the just-in-time compiled blocks, and we will be able to match them with PDB files. And then we wait for the user to stop the session. And on this, when the session stops, we need to collect rundown events. So that's the blinking moment in purview. We need to create a separate event session and use another provider, CLR rundown trace event parse provider. which which forces all the .NET processes that are running on our system to emit those meta events about just-in-time compilation and also other parts of .NET. And finally, we are okay. That was it. Finally, we are creating a zip file, and we are merging the rundown with the main ETL file, and the zip file will be in our sampler big here. So here it's the zip file that the tool created, and the analyze command. We are reading the file, so we're unpacking it. Then we are looking for the process. We are creating the trace log. That's something bigger than the trace event session that we were using for writing the events. Trace log is a very smart way of parsing the event ETL files, so ETW traces. And trace log contains some backlogging. So it collects the meta events about all the processes that were running in the system threads. And additionally, it analyzes the call stack events. And for each event, matches the call stack with the call stack event with the actual trace event. So it's a great class, and it does all the hard work for us. Because once we have the process, we need to iterate through, here we are loading symbols for this process. So we are iterating through module files, and we are using a symbol reader, which is also coming from the NuGet file. And it also does all the hard work for us because it downloads the necessary PDB files from the public symbol server, and it also resolves .NET stacks. And then I'm also loading symbols for the system process. Usually it has a PID number 4, but I don't know why. Maybe it's a bug in purview. For some reason it assigns the number 0. So once we have the symbols for all the processes, both our process and the system process, we are ready to start and build the call stacks. And maybe as the time, I'm almost done. I already passed my time. I will just show you what those methods produce. So here we have an ASCII tree that normally you will see in purview. That would be exactly the same. So the number of events for a given thread, and then the events are grouped to the max of the stack that we define here. They are grouped into a tree. And so all those things here should sum up to 136. So we can see that for the startup thread, we collected that many events. But if we look for other threads, some of them did not have any events. We have 2 events for the .NET thread pool worker, and then and that's it. So of course, I will make this source code available so you can play with it. I have also an F# version that I will publish on the blog. I actually wrote it to C#, so it maybe will be more understandable. And that's it. Thank you very much. Once again, my blog is at lowleveldesign.org, and you can connect with me on Twitter and look for WeTrace.net. I hope you will subscribe and you will be one of the beta testers and later users. So once again, thank you very much, and please ask questions.
Thank you, Sebastian, for an awesome talk. As always, very spicy and dense. We can always count on your content. Okay, so now it's the time for questions. If you have any questions, do not hesitate to ask. We have the very first question from Azet Brainiac, which is about our beloved tool, WinDBG. So what do you think about WinDBG in general? Could it be useful in .NET Core app debugging, researching, investigation?
Definitely. As you can see, I have WinDBG in my toolbar here. So WinDBG is really a great tool, and you can use it for .NET Core too. And of course, there are those quirks that you need to learn those commands, and it's a native code debugger, so placing breakpoints is not really easy. But if you need to examine the memory or one thing that I recently, I am constantly using while diagnostics is the time travel debugging. If you haven't tried that, try it. It's a really a completely different way of debugging applications. When you record the time travel debugger session, it takes a lot of space on the drive, so it can't last for more than, I guess, 20 minutes. But the amount of events that WinDBG is collecting allows you to move to the past, to the beginning when the process started, and then look exactly at the moments when the problem happened. And if you haven't caught it, then move back and try again. So something that we always dreamed about now is coming to the reality. So definitely try WinDBG and use it with .NET Core.
Right. You're talking about this preview version of the new WinDBG, right? Because exactly. We have now 2 WinDBGs, in fact.
Yeah.
And then we have .NET Dump Analyze, which is a little bit something tailored to the SOS or only debugging, but still very similar low level. Okay, while waiting for another question, I hope it will be at least one more question. I have a question. So because I'm sometimes a little bit confused about the support of the .NET runtime using both ETW or event pipes. So did they totally move from ETW to use event pipes only, or it is some providers are still using ETW, or maybe others are using event pipes?
That's actually quite interesting, because when I started working on .NET NetTrace, the oldest version of .NET NetTrace was using only ETW. It was based on ETW, and it was working fine for .NET Core 2.0. And then I tried to port it to event pipes. I found that the API could be, there is a layer when those APIs are the same. You can use the same session and the provider's API is exactly the same. However, the parsers were not working in .NET 3.0, as far as I remember. So I was not able to use the same parser for those events. Although the provider name was the same and the keywords were the same. But then in .NET 3.1, I think, they fixed that. So the parser started to work. And now the state is that you can use either of them, and you can use exactly the same parsers. So both ETW and event pipes produce the same events.
So
I'm not sure.
Both mechanisms are is still supported, and it is up to you whether you want to use ETW or in case of Windows, and then event pipes on both systems, right?
Yeah, that's what I observed. Yeah.
That's interesting. Okay, we have a question about it's about okay, it's the good question to the author, so it will, right?
Yeah, but thank you for using it. And the next release will work on Linux it will work for Linux for .NET events, and not yet system events. I'll be working on that. I plan to use eBPF for those events, so yeah, I hope I will have it. But it will work for .NET.
Right. Awesome. And so still, while waiting for maybe one last question, another one is when you were showing from me, when we were showing .NET Trace, can we list somehow providers from a process? Well, like you did what to type, like there is a provider for HTTP, there is provider for this, for that. Is there any way of, because they are not one-to-one to the ETW providers, right? Or not? How it is? Can we list it somehow?
Okay, I'm not sure about it if they are one-to-one mapped, but yeah, that's a good question. I'm not sure. I think that it should be possible because you could open a very short trace session because you have the PID and then collect the manifests. They are the first events that are coming in the trace session, and then stop the session and look through the manifest to check which providers are available. So maybe
sounds
that's
like a good tool. Global tool for .NET. Exactly. No, but in the, because it is good to know what you can trace, right? So it should be probably we can rely on documentation or something. Okay. Another question from cookies. So from our friend, and I believe.
Actually, I haven't mentioned, but both Christoph and Kevin have great articles on Medium.
Sorry for skipping your question, but this tool for webinar just show it me now. So yeah. The question is whether it's supporting managed debugging.
It works. I mean, from the WinDBG perspective, it's just collecting the native. I mean, I haven't examined exactly how it works. I know that it uses drivers, so it must be some hardcore things going on there. But it records all the steps that are happening on the CPU. So I did debugged a managed application with TTD, and the only it was not working only when the application was. I mean, there was another application that was injecting something into the application being debugged. So, for instance, when there was some, I'm not sure about profiler if it's that invasive, but if you had some hooks or this kind of interference, the WinDBG time travel debugging was breaking. But if the application was just a normal application running in the system, it was running fine. Of course, there are some issues with TTD, and I remember that when I tried to trace a system process such as LSAS, for example, I know it's stupid to trace LSAS, but to debug LSAS, but I tried that, and I remember it was breaking sometimes. So, but generally it works. And especially when you have a short scenario that you need to debug, then it should be fine. I mean, it should be working.
Sounds worth trying for sure. Awesome. And we will provide the presentation showed today, right? So we will link it in the description of the video, so you can use it. All the tools mentioned by you. By the way, most of them are open sourced, right? Purview is open sourced.
Except for sysinternals, the rest is open source.
Unfortunately, right?
Yeah, unfortunately.
We are waiting all for that. Okay, so let's look at the chat, whether there are any other questions. I don't see any questions, so you have just missed an opportunity to ask any more questions to Sebastian. You can always meet Sebastian on YouTube. Not YouTube, on Twitter. You are just there as a low-level design, right?
Yeah.
Twitter handle. So we also link it in the description. So I believe it's time to end. If we don't have any more questions, it was awesome to have you. Thank you all for being here. Thank you for talking, giving the presentation, and see you tomorrow then.
Yeah. See you. Yeah. Bye.
Bye.